you can see that it has stripes, right? Jupiter's kind of known for its stripes. And notice that the stripes are rotating different directions. The image on the right, you can see that Jupiter has aurora. So Jupiter has a magnetic field just like we do. And the ions from the sun crash into the thermosphere of Jupiter and spark aurora just like on Earth.
Wait, that's real? That picture is real?
They're all real images.
Whoa.
If you put the red spot in motion, it's just like a storm on Earth. In the northern hemisphere, our storms all rotate counterclockwise. So we've got these 5 tropical storms right now in the Atlantic. One of them is about to hit Louisiana as hurricane status. And the only difference between a tropical storm and a hurricane is wind speed. And once it hits 74 miles an hour, it's a hurricane instead. They keep the name and everything. So anyway, I think, what is it, Sally? Is that the most recent one? I think Hurricane Sally is going to strike Louisiana here real soon. But if you look at all these storms on the radar, they're all spinning the same direction, counterclockwise. And the Great Red Spot spins counterclockwise, but you see the layer that it's in is moving a clockwise direction from the perspective of the South Pole. Anyway, I don't want to talk about Jupiter all day long, even though it's interesting. I want to talk about the Earth. If I were to ask you, does the Earth have stripes? Does the Earth have stripes? You'd probably say no, right? I mean, Jupiter's the striped planet. Do other planets have stripes? Well, it turns out that the Earth does have stripes. We have stripes exactly like Jupiter's. We just don't see them. Ours are invisible stripes. So you have to believe me that they're there. I'll prove it to you through this lesson. The only reason we don't see them is because our atmosphere is not thick enough. Jupiter is almost all atmosphere. And so the chemicals in there show up better. But because our atmosphere is very thin, it's only when we have really thick cloud coverage that we see our stripes. So let's get to that. Okay, here's the boring stuff, but this is crucial to you understanding everything. The meaning of life is today's lesson right here. All right, remember that the equator is hot. Do you remember why it's hot? The answer is it gets the most direct insolation, the most direct sunlight for the majority of the year. And it's between the tropics, 23.5 north and south, that all year long they are getting almost 90-degree sunlight. Hot air expands and rises because it becomes less dense. You can see off to the right, that's what's happening. It says thermal equator, warm, moist air rises. So as it expands, it's taking moisture with it. And eventually it rises up high enough that it cools down as it spreads out, and then it starts to drift either north or south. So what I'm describing now is the beginning of what you see there called the Hadley cell. The Hadley cell is a giant convection current that takes warm, moist air away from the equator and pushes it up toward 30 degrees north and 30 degrees south. It's called the Hadley cell because that's who discovered it. When air heats up and expands and rises, it cools. Cool air can't hold as much moisture, and so it has to dump it all out as precipitation. So that's why you see the storms and clouds just north of the equator. So the Amazon rainforest is there because of that warm air rising and the low pressure band going across. Every 30 degrees, the pressure belts on Earth alternate. So if you look at 30 degrees north and 30 degrees south, they're both high pressure, blue skies, dry air, because all the rain already came out. And as the air heats back up and sinks, it's incredibly dry. And College Board wants you to know that at the 30-degree marks, we have deserts on Earth. So the middle of the Earth is tropical, but on each side, we have strips of desert biome. There's one other thing you should understand, and it's the arrows that are on the globe. Those are the winds. We're going to really talk about wind today. Wind is caused by what we call differential pressure. A change in pressure causes wind. And here's a rule you can always remember. Wind always moves from high pressure to low pressure. So we see that the winds move from 30 degrees back to zero because low pressure is in the middle. We call these the trade winds. And they got their name because they're strong, steady winds that we can count on to do trade across the oceans. So these patterns don't stop at 30 degrees. These patterns continue every single 30 degrees all the way up to 90, the poles. At 30 degrees, the horse latitudes, the winds move apart. The pressure bands just alternate. If I start at the pole, it's high, low, high, low at the equator, high, low, high. They alternate every 30 degrees. And so that means there's always a wind either moving away from it or coming toward it. The winds that go over the United States, they are marked in red, and they are right above the horse latitudes. Because they come from the west, they are called the westerlies, the prevailing westerlies. That's how our weather kind of works in the United States, right? Whatever happens in Illinois, we typically get the weather after them. Our weather pushes across from west to east. If we look at the northern hemisphere, do you see how the winds kind of go in a circle? They kind of go up and back and up and back. And look at the circle in the southern hemisphere. You see how they kind of go in a circle? But did you see what's different about them? In the northern hemisphere, they go clockwise. And in the southern hemisphere, they go counterclockwise. This is called the Coriolis effect. The Coriolis effect is a result of being round and spinning on our axis. If I stood at the North Pole and I threw a baseball straight at the equator, the yellow line, that is not where the baseball would end up. I'm not strong enough to throw it that far. But if I could probably get it to Mexico. If I could throw it that far, it would actually end up where the red arrow shows. And that's because the Earth would be turning underneath it, right? So it's going to end up skewed to the right because we rotate that direction. So look at that. Our winds in the northern hemisphere all bend to the right. And it's the opposite in the southern hemisphere. Every wind bends to the left. Here is the northern hemisphere, right? And we turn into the sun. So we're rotating this way. And the sun comes up first in New York. And then we spin, right? It's not the sun moving, it's us moving. We spin, and then the West Coast is 3 hours behind us and so on. So we're spinning this direction, okay? That's not shocking to anybody. But watch what happens if you watch it from the North Pole. What direction are we spinning? We're spinning counterclockwise, right? That is the direction we spin. You ready for this? Watch what happens when I show you the South Pole. What direction are we spinning? Did you see it switch? It's like an optical illusion. We're spinning one direction, and then everything goes the opposite direction when viewed from the poles. So that's the Coriolis effect. If we weren't round, everything would spin the same direction.